The purpose of this lab is preparing two pieces of charge clear tape and observing how they interact, determining the approximate excess charge on one piece of tape experimentally and computationally by making estimates and simplifying assumptions. The main physical principles involved in this lab are Newton's first and second law and the force of gravity near the Earth's surface, as well as the concept of electric charge and Coulomb's law. By collecting data and through hand calculations and a computational model, a rough estimate was found for the charge of the tapes and for the electron deficiency in each tape. It was thus found that the charge of a tape can be estimated experimentally, but there are questions on the accuracy of the methods used in this lab. Ordinary objects can acquire an excess or a deficiency of negative charge if they are rubbed, pulled apart, or if they touch other objects. With a simple experiment, we can determine the amount of excess charge on a tape to within an order of magnitude, giving a sense of the amount of excess charge on regular objects under normal conditions. For the experiment, we need a roll of clear tape, a ruler, a flat surface, and stackable objects for support. First, we stick a 20 cm strip of tape down onto a smooth table, making it non-sticky. Then we stick a second strip on top of the base tape smoothly, and quickly pull the upper tape off the base tape, leaving the latter stuck to the table. If we make a second tape and put them together, these repel as they must both have an excess or deficiency of electrons. If we bring a negatively charged pen that has been rubbed on clothes close to a charged tape, these will attract. The tapes are thus positively charged. Hence, we can estimate the charge on the tape by floating one piece of tape on top of the other. As shown in the setup, one strip of U-tape can be fixed to the supports. This will come on its own due to gravity. If we place a second U-tape below, the fixed tape will tend to return to its original shape because of the repulsive interaction between the tapes. Considering the system consisting of the fixed tape, the main elements of the surroundings exerting force on the system are the bottom tape, which exerts a repulsive electrostatic force on the system, and the earth, which exerts a gravitational force on the tape. At a separation d between the tapes, the forces acting on the system are balanced, yielding a net force of 0 newtons. Assuming that all the charge on the tapes is concentrated in the center of mass, the following model should be satisfied. As the forces should be equal in magnitude, we can solve for the charge in one of the tapes. We measured that the forces were balanced at a separation of 25 millimeters. Assuming that the tape has a mass of 1 gram per meter, the mass of a 0.2 meter strip of tape is 0.2 grams. Plugging in these values, the estimated charge of its tape is roughly 12.67 nanocoulombs. Dividing the overall charge of the tape by the charge of an electron, we estimated that the electron deficiency of the tape is roughly 70 billion electrons. Assuming the tape is a 1D object, we can estimate the number of atoms in the tape and the ratio of atoms to lost electrons given that the atom measures roughly 1 angstrom. This gives us a ratio of 37 lost electrons per atom. For the computational model, we set up the constants and the objects with their initial conditions, including their mass, their position, and their properties. A function is defined to calculate the gravitational force on the floating tape, and then the charge is estimated by using the model. Finally, the number of electrons lost by the tape, as well as the ratio of electrons lost to the number of atoms, is calculated. The results obtained with the model match those from the hand calculations. Some sources of error include that the tape is modeled as a point charge, but in reality the charge is distributed over its surface. This simplifying assumption can make the actual and calculated values differ significantly. Other errors might be that the bottom of the tape was not held parallel to the floating tape. The setup makes it difficult to measure the distance between the tapes accurately, and modeling the tape as a 1D object can cause major imprecision in the number of electrons lost per atom calculation. If electrons had positive charge and protons had negative charge, like in the case of antimatter, they would still repel because they would both acquire a deficiency of positive charge by ripping them off of the base tape. However, the charged tapes would be repelled from a pen that has been rubbed in cloth, as in this case they would both be negatively charged. It is important to handle the tapes as little as possible and from the edges, because if not, charge transfer can occur between surfaces and the results could be inaccurate. To sum up, objects can become charged by physical interactions with other objects, like rubbing or just by making contact. The charge of a tape that loses electrons when pulled from another can be estimated by holding a second charged tape underneath and measuring the separation at which the electrostatic force and the gravitational force on the floating tape are balanced. The model used in this lab provides a rough estimate that can differ significantly from the real value as many simplifying assumptions are made. The handling of the tapes can also lead to inaccuracies and the inability to reliably reproduce the experiment.